Hello and welcome. In this video, we're going to take a look at a technique of integration called substitution. Now, the method behind substitution is derived from the chain rule. So let's start off by reviewing what the chain rule was from differential calculus. And remember that if we have a function inside of another function, something like f of g of x, which we call a composition of functions, then when we take the derivative of f of g of x, we need to take the derivative of f with respect to g, and then we take the derivative of g with respect to x, and we multiply. So with that in mind, how do we reverse the chain rule to look at an antiderivative of something of that form? The substitution rule, as in a very technical definition here, is if we let u equal some function g of x, and if that function is differentiable, meaning its derivative is defined, and let's suppose that its range is an interval I. And f, that's our outside function, f of g of x. F, let's say, is continuous over that interval of all of the values for which we get. The substitution rule, as a more technical definition, is where if u equals g of x is some differentiable function, meaning its derivative is defined, whose range is an interval I, meaning that all of the values that we get for output from that function are within an interval I. Let's suppose that f is continuous over that interval I. Then the derivative of u, du by dx, which is simply g prime, can be rewritten into this differential form. The differential of u is equal to g prime of x times the differential of x. Kind of like treating du by dx as a fraction. Now, when we do that, whenever we have the indefinite integral of f evaluated at g of x multiplied by the derivative of g of x, well, that kind of looks a little bit like a chain rule. And what we can do is, by introducing something new, we let u equal g of x, then our function, instead of having a bunch of x's in there, we can replace g of x with just u, and that's going to change the variable to u. Now, the remaining part of our integral, g prime of x dx, that can be replaced with du. And we end up with a brand new integral where we simply have a function of u, and it is being integrated with respect to u. So we're introducing this new variable to eliminate the need for a composition of functions anymore. We should end up with a nice straightforward function of just one variable u, and hopefully it'll look kind of like one of the many rules we've learned so far. Power rule, exponential rule, 1 over x rule, that kind of thing. Now, this is just a more technical description of the substitution rule. Let's see what this looks like in practice. In this example, we see that we have a function x squared plus 5 inside of another function, the x cubed function. In this example, we see we have a function x squared plus 5 that is really inside of another operation, something like u cubed, where u is this x squared plus 5. We can also see that the derivative of x squared plus 5 is 2x, and we have that being multiplied right after our u cubed component. So this kind of leads us to indicate that we could make a substitution here that if we just let our x squared plus 5 be a new variable, we'll introduce u, for instance, then by letting u equal x squared plus 5, we can see that we actually have du by dx as well. So we'll have to do a change of variables, and we have to decide on what our new variable is going to be. Oftentimes, we can use u safely since it's not being involved in the problem already. But whatever our substitution variable is, it needs to be some variable that's not already having some kind of meaning. So we'll let u equal x squared plus 5. Now that's going to let our integral simply be a function u cubed now. So you see that there's no composition of functions there anymore. It's simply just a function of u. Now, what about this 2x? Well, this is where we take the derivative of our substitution. Du by dx is equal to g prime of x. X squared plus 5 is our g of x. The derivative of that is 2x. And then we write this in differential form. We actually just say that du is equal to 2x dx. And so we can make a replacement with 2x dx as just being du now. Now, these integrals are equivalent because behind the scenes, we are actually disguising the fact that u is just x squared plus 5. This makes the integral easy to solve just by using a power rule, raising the power by 1 and dividing by the new power. Make sure that we also add our arbitrary constant of integration, but then we're not done because this is just an equivalent solution. We want the solution or the answer to the original indefinite integral. We need to replace u with x squared plus 5. And there we go. We've got the most general form of the antiderivative. And if we check this, we can take the derivative of our answer and see that we end up with x squared plus 5 cubed. Now, this indefinite integral was deliberately set up so that it would be a very obvious choice for our substitution in the fact that that derivative of that substitution 2x was immediately apparent. But that's not going to be usually the case. Let's try a couple other examples where we may have to be a little bit more clever or have a little bit more manipulation when we make our substitution. Well, in this example, we've got some sort of fraction here. We've got 6x squared in the numerator, and we've got the square root of x cubed plus 1. It's not immediately obvious how a substitution might make this look simpler. But when we're choosing a substitution, if we think back to the substitution rule, our u equal g of x should be chosen so that it is a function inside of another function. And so 6x squared is a great function on its own. It's simply just placed up there in the numerator, though, which is about the easiest place that we could have a little polynomial. But we also have a polynomial x cubed plus 1, and that would be just simply easy power rules if it wasn't for the fact that it is inside a square root. So it might make a lot more sense to let u equal x cubed plus 1. Now the issue here is that when we look for du by dx, we end up with 3x squared. Well, I don't have 3x squared, but in the numerator I do have 6x squared, and the fact that they both have x squareds in them makes this a great substitution. Now, we can manipulate this a little bit so that we can get this in differential form. Du would equal 3x squared dx. Well, if I have 6x squared dx, then I would actually technically have 2 du in my integrand. But one method that I sometimes prefer to do is simply rearrange so I can make a substitution for dx. And if dx is equal to du over 3x squared, then when I plug that in, I can substitute my dx with du over 3x squared and make sure that the x squareds will at least cancel, leaving me with a function of u. So that 6x squared is going to hang out there for a moment. My denominator is now a function of u, which is good. Unfortunately, I still have a function of x in the numerator. But that can be fixed by making the substitution dx is equal to du over 3x squared. Now you should see that the x squareds cancel, and 6 over 3 becomes 2. And there we go. That's kind of the goal of substitution here, is to take some sort of integrand that is a composition of functions, probably with multiplication in there too, where we have a multiplication of some other function which is the derivative of the inside function, and turn that whole integrand into a single function of u, making sure that we don't have a lot of composition anymore. We just simply have a nice basic form. Now, what kind of form is this integral? We've now got a form of 1 over root u, but that's okay. We can write that as a power. Firstly, we can move the 2 outside of the integral and write the integrand as 1 over the root of u du, and of course that becomes a power. Rewriting that as u to the negative 1/2, we'll have to raise the power by 1, which is 1/2, and then when we'll have to divide by 1/2, we can multiply by the reciprocal. And the reciprocal of 1/2 is 2. So the antiderivative of u to the negative 1/2 is 2u to the 1/2, and then we can't forget to multiply that by 2, and we'll add our constant at the end. Now, if you wanted to be technical, we could say that that constant really comes from the integral and then needs to be doubled. But much like adding multiple arbitrary constants, if we take an arbitrary constant and we double it, it is still going to be a constant. So regardless of where we put the brackets there, we can still treat this as just plus some constant. And then our final answer can be written as 4 times the square root, replacing u equal x cubed plus 1 back in, we end up with a square root of x cubed plus 1 plus c. And again, you can check your answer here using differentiation and see whether or not we get our 6x squared over the square root of x cubed plus 1. In this third example, I have the integral of a product, 3u times e to the negative u squared with respect to u. Now, we do have a product here, and maybe your first inclination is product rule, but, well, product rule for integration is not the same. We will actually take a look in a future video about how to reverse the process of a product in your integrand, but that's okay. We still also, even when reversing the chain rule, when we're using the substitution rule, we should see some product in there. What we're looking for is, first and foremost, some function inside of another, and then hopefully we see that we also have a factor in our integrand, which is the derivative of that inside function. So if you take a look, we do have this negative u squared, which is a polynomial. It's simply a power, but that is a polynomial inside of an exponential function. So it might make most sense to make a substitution for negative u squared. Now, what the heck? I actually used u as the variable in my integral. Why did I do that? Well, the purpose of me throwing a curveball there is just because, what if your integral already uses the variable u? You're doing substitution, you need to introduce something new. You can't reintroduce u if u is already in your problem. So I guess we'll have to choose something else. Already used u, why didn't we use v or some other favorite letter? And if you are sick of using a whole bunch of the same letters all the time, that's why we got a whole other alphabet. Why don't we use some of the Greek letters? It's really up to you. And this can happen. Sometimes we have to do substitution maybe multiple times. And by doing a substitution, you'll probably have gotten a new integral with u. You have to do substitution again. Then we have to choose another variable. Problem is, of course, probably you'll have to go and resubstitute back twice at the end. Anyway, let's just take a look and see what happens. Why don't we choose something like v? Make sure that your v's don't look like u's. It's going to happen eventually. Let v equal negative u squared. That means that dv by du is equal to negative 2u because, we're taking the derivative with respect to u now. And that's okay. We've got a 3u. It's pretty close to a negative 2u. Seeing as how the form is the same, they both have a linear factor of u. I think this should work out well. We're just going to replace du with dv over negative 2u. So making those substitutions now, we'll have the integral of 3u. That's not good, okay? We want our new integral to be a function of v, but don't worry. We have e to the v, and du is going to be replaced with dv by negative 2u. And the u's here should cancel out nicely, leaving us with a function of v. Now this 3 over negative 2 doesn't simplify, but it can be moved out front, negative 3 halves times the integral of e to the v dv, which is always one of our favorites. And there's our antiderivative of e to the v. And finally, we replace our v with negative u squared. And so we end up in the final variable as the same variable that we started with. Now, of course, integration by substitution is a very common method, just like the chain rule is very common for differentiation. It can happen in just the smallest circumstances, even if we just have the indefinite integral of e to the 2x. You have to do a little substitution there. By letting u equal 2x, that means that dx is du over 2. And eventually we'll end up getting the antiderivative as 1/2 e to the 2x. And those kind of substitutions, they can be very quick and obvious once you do enough practice. If I have a function of some constant multiple of x, and then I look at the antiderivative, because it's a function of a constant multiple of x, like cx, my antiderivative usually has a 1 over c in front of the antiderivative. So try some practice on these. It's a very fundamental technique, and there are many other techniques of integration that are a little bit more challenging, but often need that little substitution in there somewhere. So it's really one of the most important basic techniques of integration to learn. Well, we'll see it many times in the future, I think. So thanks for watching, and I'll see you in the next video.